Hello students, today we will go little bit off bit and we will we will deviate ourselves from the space spectrum communications, and we will today learn the fundamentals of wireless communications, the concept of wireless channel, how does it behave, and what happens when signal is released from the transmitting antenna to a wireless channel. How the characteristics of a typical channel gets changed over the air, and how do we receive it in the front end of the receiving antenna. The aim of this class is to open you up about the fundamentals of wireless communication, and then after gathering the knowledge of channel and the propagation characteristics of a wireless communication, we will be able to implement the space spectrum communication on the top of this wireless communication, and hence we will be actually well literate to design the transceiver, space spectrum communication transceiver for wireless environment. And that is the final target, because this theory and all the learning over the space spectrum communications fundamentally needs to be implemented in a practical situation where the communication between transmitter and receiver will be happening over a wireless channel. So, it is a very important part to understand how wireless communication happens between a transmitter and receiver. Today we will concentrate behind that. We will also learn some very fundamental parameters associated to the wireless channel, and the probability, in terms of probability also we will try to learn actually the different models and their characteristics, their parameters of those models, all that. We will start with the fundamentals. This is a transmitting. The figure says about there is a transmitting antenna and there is a receiving antenna some distance apart from each other, and the antennas are such that for this communication the signal will be released from the transmitting antenna and expected to travel over the wireless channel, and it will be received by the receiving antenna. All the blocks that we have learned inside the receiver, they come after this signal reception by the receiving antenna. Also, the all transmitter blocks, baseband blocks, including the RF circuits that we have already learned for the space spectrum communication transceivers, they are all residing inside this transmitting block. So, transmitter blocks, whatever you have learned is inside this block box. Whatever the receiving blocks you have learned till now, they are inside, suppose they are inside this receiving block. Remember, when we talk about a wireless channel, technically there are two different kind of the channels that we consider for our discussion and for our analysis. One is the propagation channel. The propagation channel is the channel in between the transmitting antenna and the receiving antenna. I mean, excluding any RF circuitry and the antenna itself incorporated in it. But when we talk about a radio channel incorporates the propagation channel, I mean the air that you see, and also includes the antenna and the antenna parameters, as well as a little bit about a backup circuit of this antenna, so that the signal can, the circuit that are helpful to just release the electromagnetic wave. And so this is the radio channel. We will see that several times we will utilize terms as radio channels, and sometimes we will talk about the propagation channel. The difference between them is like this. So, what happens when an electromagnetic wave is released from a transmitting antenna? The wave, once it is released, he actually traverses. If it is a omnidirectional antenna, the wave will be released over 360-degree angle. And remember, the part of this energy only will be traveling towards the direct line of sight path, and will be reached to the receiving antenna like this. So, if I think that I can draw the electromagnetic waves by some rays, So, this is a direct ray that is reaching from the transmitting antenna to the receiving antenna. We call it a line of sight path. Okay. And what happens to the, is there any other paths available? It is, yeah, it is there. And over the air on the wireless channel, you will see that lot of the scatterers, I mean if it is outdoor communication going on, then a lot of the high rise and all other elements and the scatterers present in the environment, they will be actually responsible to give you the reflected rays after when the electromagnetic waves hit them, and they are sent by them, the scatterers, and like this. So, there are several scatterers, and for each and every scatterers there are the scattering rays, the scattered rays coming actually from each of them, from each of their points, and over multiple scatterers, over multiple scatterers present in the environment, you are expected to get the huge number of the multiple paths to arrive in the receiver front end. So, thing is that you released suppose one symbol, and now you are with respect to that symbol, you are continuously going to receive the related electromagnetic waves for corresponding to that symbol over multiple paths. So, the same symbol getting received in the receiver over traveling over multiple paths. It is a unique phenomena that is happening inside the wireless channel, and this basic propagation, we call it the propagation of the waves, electromagnetic waves, and this basic propagation is basically controlled by the reflection, the diffraction, and the scattering. These are the three fundamental phenomena that happens, and they create the multiple path to the communication system. And remember, all the paths which are not coming via the direct way, we call it the non-line of sight paths. They are NLOS paths, and these are called also the multiple paths. And remember, for all these paths to exist in practice, we have obviously the time that is associated over each and every path for the signal to traverse from the transmitter to receiver are not same. It is obvious that the time elapsed over the line of sight path to for a signal to reach from a transmitter to a receiver will be the least, and say if it is a tau 1 time, then for the next one, say for another path, it may be the tau 2. After this delay, this is the time elapsed for the path for the wave to reach from the transmitter to receiver after scattering, and like that each and every path is associated with their corresponding delay associated to it. And thus I can see actually the replica of the same symbol getting received in the receiver front end over a multiple delay. So, it is a replica of the same signal continuously coming over the different delay to the receiver front end. And if I try to plot it in the receiver front end, we call it and we try to see how the power is getting received here in the receiver front end. So, it is expected that after tau 1 I will receive one path, after tau 2 I will receive one path, after tau 3 I will receive another multiple path. As the delay is varying, as the same way the power that you are getting received, that power will also vary. The maximum power it is expected to receive by this direct path, and whenever depending upon the characteristics of the scatterer and the angle of also the angle of your direction of arrival to the scatterers and the direction of departure from them, based on all that phenomena, your amount of the power that you are going to receive by that via different multiple paths, that will be different. So, if I try to plot the received power, so the tau 1 if it is the line of sight path power, so I will have maximum power at that moment, followed by the next immediate multiple path who is arriving, and he may have a relatively smaller power, and then the third one, and it will go on like this. So, if I try to see the profile, then this is a power, received power. So, we call it a power delay profile, where actually in the x axis you are plotting the delay of arrival on multiple paths and you are plotting their corresponding power values. You will see that the power will be exponentially having exponentially decaying profile in a wireless communication, and most of the cases we will see that, but it is not the only profile that we find in a wireless environment. We see lot of other profiles also, but most general cases we see where the line of sight path is there, we see this kind of the profile for the power, received power in the receiver front end. Now, the power that we have received here. So, if there is a free space, suppose in the free space how the power will be received, it was given by Freeze, and according to him, if the transmitter and the receiver is having a distance of d, the received power in the free space, the front end of the receiver will be given by this formula, where actually the PT is the transmitted power, GT is the gain of the antenna, transmitting antenna, GR is the gain of the receiving antenna, it is the wavelength of the transmission, and lambda is equal to obviously CYF, and this is a constant parameter. D is the distance between transmitter and receiver, and capital L is the loss associated with the RF front end, but it has nothing to do with the propagation. But for propagation, all other parameters that are involved to decide the received signal power level are these are the parameters. So, see, actually the received power is a function of the transmitted, not only the transmit power, it is a function of the transmitted transmit antenna gain, receive antenna gain, the frequency of transmission, and the distance between transmitter and receiver. And let us come back again inside the channel, and if I see this channel can be mathematically modeled by lot of ways. Usually when the signal is propagating through a channel, we understood that because of reflection, diffraction and scattering, because of these three phenomena, lot of changes are expected to happen over the signal property. It is not only that the power is decaying, it means the amplitude of the signal, of the received signal, is differing from the transmitted signal. So, there is a change in the amplitude of the signal. There is also a change over the phase of the signal. So, remember the phase with which you are releasing it, that won't be the same after scattering over the multiple paths. So, there is a phase change happening inside the channel. Also, if the transmitter and receiver, they are moving with respect to each other, because of the movement the Doppler effect will come into picture, and it is expected that there will be a change over the frequency also. So, there are a lot of things happening over the signal. The signal is getting dispersed over the time, because the multiple replicas are expected to come. So, the same signal is now getting spread over the time duration up to T3 or tau 3 or tau 4 or tau 5 till it is the replicas are expected to come. So, signal is not confined on this time interval, signal has got dispersed over the time. Signal will be dispersed over the frequency because of the Doppler effect. When transmitter receiver will be moving, any one of them will be moving or both of them will be moving. And on the top of that, there are a lot of parameters that causes the environmental changes of the wireless channel itself, which will also have some impact on the received power level. And as an effect of all that and these basic propagation mechanisms, you are expected to get lot of changes on the amplitude, time, phase and frequency of the received signal. And all these effects, we can actually divide that effects broadly under the large scale effects and the small scale effects of a channel. The large scale effects basically consider the path loss and the shadowing, and this large scale model basically actually predict the mean signal strength that you are receiving for an arbitrary transmitter receiver separation. So, when we talk about a large scale model of a wireless channel, basically we give the output as a mean signal strength over an arbitrary transmitter receiver separation. That is a long term, over the long time duration also that large scale effect holds good. But the most important part that where our interest lies in the wireless communication is the small scale effect. And the model, wireless channel model, which captures the small scale effects, basically actually this model predicts the rapid fluctuations of the wireless channel that is happening, and its reflection, hence its reflection on the received signal strength over a short distance that is happening is captured by the small scale fading model, propagation model. This small scale effects basically we call in terms and by a term called fading, and this fading is basically of several types in a wireless channel. We realize it may be flat, it may be frequency selective, it may be slow, it may be fast, and we will discuss about all this in the next slide. And the model sometimes also captured the polarization effects of the antenna, whether it is vertically polarized or horizontally polarized or it is circularly polarized, and based on that the model will be much more critical. So, for our basic understanding we will mainly concentrate inside the small scale fading effects and the small scale channel models of wireless communication. So, as I told that small scale fading or simply fading, actually it is used to describe the rapid fluctuation of the amplitude of the received signal over a short period of the time and also for a short travel distance. And fading is caused by why the fading is coming up, because there is an interference between the two or more versions of the same transmitted signal that are arriving in the receiver over the multiple instance of the time. So, for the basically the thing is something like this: when you have received the first line of sight path for say signal 1, and if you are having a sample duration equal to the say multipath arrival duration, say second tau 2 you are receiving when you have sampled tau 2, tau 3, tau 4 at a gap of that, and suppose you have received the fast signal line of sight path here, then its replica is also expected to come here via the second multipath. His replica is expected to come here, his replica is expected to come here, it is going on. But by the time if it is a continuous transmission going on from the transmitter, during this tau 2 interval also you are going to release the second symbol, and his replica is also expected to come during this tau 3 and tau 4. In tau 3 you have already released the third symbol, so his replica is also expected to come in S3. So, you see at each and every timing instant, delay instant I should say, there is a very complicated signal model is you are going to receive. The addition of the multiple signals with their corresponding changes in the amplitudes and phase, you are expected to, its additive effect, you are expected to receive in the receiver front end. So, this combined phenomena or the changes of the original signal because of the other signals that are coming, that are superimposing on it at the receiver front end, is termed as a term fading. Remember this, the main causes, the most important effects of this small scale multipath propagation is that the rapid changes in the signal strength over a small travel distance, a very random frequency modulation that will happen because of the Doppler shifts on the different multipath signals, and dispersion because the echoes are expected to come over the multiple propagation delays. So, these are all about the small scale multipath propagation, that is a common phenomena about inside a wireless communication channel, and these spatial variations of the signal over a wireless over a space in a wireless domain, it is seen in the receiver front end as a temporal variation that we have explained here. So, this is about the fading, and let us quickly visit how many types of the small scale fading we encounter in a practical communication system. Small scale fading, if I classify it based on the multiple time delay spread I wrote it in terms of tau. So, if it is a with respect to time delay spread, you will get two part. One is a flat fading, another is the frequency selective fading. What is flat and what is frequency selective, we will discuss in detail later on. But fundamentally, just remember that flat fading happens if the bandwidth of the signal transmitted is less than the bandwidth of the channel. Then you will encounter that all the signal components are experiencing the same kind of the amplitude change and the phase change by the channel. We call it the flat kind of fading. And if this is not, I mean the bandwidth of your signal is higher than the bandwidth of the channel, then channel is expected to behave different way over the different portion of the signal, and hence the amplitude changes and the phase changes over the different part of the signal that you will be able to see in the receiver front end won't be uniform, and it will be definitely different from the part by part, and we call it the frequency selective fading. So, different part of the frequency of the signal is expected to get a different amount of the amplitude and phase change, and hence we call it a frequency selective fading. We will discuss all this again in the later slides. Small scale fading based on the Doppler spread. This is related to the movement, and some velocity of the receiver is involved with respect to the transmitter, and because of which the received signal frequency actually it spreads, and because of that we call it the Doppler spread, and that incorporates, that brings the two different kind of the fading concept in the received signal. One is the fast fading, another is the slow fading. The fast fading is coming and related to the very high Doppler spread, and this is definitely a low Doppler spread. To understand what is fast fading and what is the slow fading, we have to understand something called the coherence time. What is this? We will come in detail. And only point to remember here is that this is something related with the symbol period. It is not the bandwidth of the signal, it is the symbol period. If the period of the symbol is more than the coherence time, I mean the time over which the channel gives channel coefficients or the channel properties does not change. So, that is the time we call as a coherence time. If that time is less than the symbol time, so you are going to get the very fast fading. So, channel will keep on changing. It is a time varying nature of the channel. Question is for how much time channel is giving you a fixed kind of behavior. Fixed behavior, I mean that same kind of changes over the amplitude and the phase you can expect over how much time is defined by the coherence time. If your symbol period is more than that time of the channel, then you are expected to get different amount of the fading, and we call it a fast fading. And opposite is the slow fading, because your coherence time, the time over which channel is remaining constant and not giving any kind of the change, it is showing uniform amount of the amplitude and the phase change. If that time is more compared to your symbol time period, then you will see the very slow fading. So, we will slowly enter into the different parameters that are associated with the mobile multipath channels. The parameters are basically the channel with respect to channel, it is a time dispersion parameter, the coherence bandwidth and the coherence time. We need to actually clearly understand the terms because we will repeatedly be using it in the system design. The time dispersion parameter basically it is the fact that we have already discussed that the replica or the echoes of the same signal or same symbol is you are expected to receive in the receiver over a large time delays. And because of that we are saying that there is a dispersion is happening, the signal is getting dispersed like this. So, signal is not like, even if you have transmitted the signal like this, now it has got dispersed like this. So, it is a time dispersion happened over the signal, and hence we define some parameters over this dispersion, which is called the mean excess delay, the RMS delay spread and the excess delay spread over the power delay profile. And remember, the mean delay and the delay spreads, they are expressed by the term tau bar and the sigma tau. They are very important to understand because we need all this arrival of the multipaths are very random process. I told that the profile will approximately follow the exponential decay profile, but where will be the mean of this guy and where will be the RMS delay spreads or the RMS value of this spread, that is very important for us to understand, because based on this mean value and the RMS delay spreads, we were going to define the lot of characteristics of the channel. And as this is a random phenomena, the arrival of the multipaths are random phenomena, and how long will they keep on continuing coming continuously, that's also is a random phenomena. Hence we define this two parameters to understand the randomness associated with this multipath profile. One is the mean excess delay, another is the RMS delay spread. We will first quickly look into the power delay profile here, and see here in the power delay profile we are seeing that this is the maximum signal, maximum power came, and these are the slowly decaying profiles came. So the mean delay is something that we have to calculate on the top of this. This is the RMS from, if this is the mean value, then this is the RMS delay spread, I mean how much the deviation is happening with respect to the mean value. What is this mean excess delay is about? It is about some extra amount of the delay for which actually we are thinking that the power will be considered to be down by certain dB level, and that is the maximum excess delay that we are trying to do sometimes, which is the point where if I am finding the second level of the threshold on the power delay profile, and if it is going down by that, when the power is going below that power delay value, so that is the maximum point of the delay we should wait for to capture the energy from the channel in the front end of the receiver. So we will quickly revisit all the points, all the elements. What is the mean delay? So mean delay is basically given by this expression, where you are taking the, for each and every path k, you are taking the power of that path multiplied with the delay associated with it, and you are averaging it over the power, total power of it. So that's the mean, and the RMS value will be actually the delay square bar minus the tau bar square, where this delay square bar is basically now the squaring up over the each and every delay path. And remember that whenever we are continuing about this delay and the measurement of the delays are going ahead, fast detectable signal, we consider that it is arriving at the delay equal to 0. That fast arrival signal may be here. So our 0 will start from here. So that it is a time axis, so actually with relative to the all the delays are measured with respect to the arrival of the fast detectable path in the receiver. So quickly come into the domain, that was the expression for the channel in the time domain. If we come to the frequency domain, you can get an equivalent description, and here we define the frequency domain coherence bandwidth, and which we use to characterize the channel in the frequency domain. Like the time dispersion happened, it is there is a very good relation between the delay spread, RMS delay spread in the time domain, and the coherence bandwidth. And we consider that if the coherence bandwidth is basically the bandwidth over which the statistical property of the channel will be remaining constant, and channel will behave as a flat channel. Flat means the channel, all the spectral components that will pass over that bandwidth, you will actually get equal amount of the gain, attenuation, and the linear phase change. And in other words, you can also say that it is a bandwidth, coherence band. It is the range of the frequencies over which the two frequency components will be heavily correlated, and amplitude correlation will be there. And if I consider that this correlation is about 90%, then the coherence bandwidth and the RMS delay spreads are related approximately by this equation. If you consider it to be a 50% of the coherence is observable between two frequencies, then this becomes consideration, then this bandwidth BC will be approximated by 1 by 5 sigma tau. So now we understand that this coherence bandwidth and the delay spread, they give about the idea of the time dispersive nature. The delay spread is coming totally related with the time dispersion, and from the RMS value of the delay spread we calculated coherence bandwidth. So it is totally talking about the time dispersive nature of the channel in a local area. but it is not giving any idea about the frequency dispersiveness over the channel. And that will be coming from the fact that there is a Doppler spread happening, and there is a concept of the coherence time associated with the channel. What are they? The Doppler spread is basically mentioned as BD here. It is a measure of the spectral broadening that will be coming up because of the time rate of change of the mobile radio channel, and it is defined as the range of the frequencies over which the received Doppler spectrum is non-zero. So, take an example. Suppose I have transmitted a pure frequency FC single tone. Because of the presence of the Doppler space shift, which is called the FD, the FC will have actually the component after passing through the channel. It will have the component of FC plus FD, and it will also have the component of FC minus FD. So, its bandwidth is now spread from FC minus FD to FC plus FD. So, FC plus twice FD is the total bandwidth over which actually now the consideration should be going ahead with, and this is the total bandwidth. This whole change, it is a measure of the broadening, it is a spectrum broadening happened, and this is called the received Doppler spectrum. And remember one thing, that once we understand that this has happened, then we can really correlate this Doppler shift, the maximum Doppler shift, with respect to the velocity that you are having in the channel, with the velocity of your mobile receiver that you are having. We can actually compute the coherence time. And though there is Doppler shift and the coherence time are just the inversely proportional with each other, but fundamental meaning of the coherence time is that it is a duration over which the Doppler's it is a time domain dwell basically of this Doppler shift, but it means that it is the time period, it is a time actually the statistical measure of the time duration over which the channel properties are again remaining invariant. For example, it is after how much time the channel is expected to be changed, as simple as that. So, by coherence bandwidth we define that it is a bandwidth over which after which the channel property is expected to be changed. Coherence time talks about the time after which the channel properties are expected to be changed. And we can have several combinations of all this while in a multipass situation. For example, delay spreads can lead you to time dispersion and frequency selective fading. You can get a frequency dispersion and time selective fading. So, we take a very quick example of a flat fading and the frequency selective fading. This was the signal coming, and it is the channel in the black box which is having the time dispersion. It is a T which is having a T and tau are the time as well as the delay basis. It is a time varying nature of the channel, and the variation over the delay is also captured here, and this is a signal coming out. So, the relative bandwidth of the signal and the channel is like this. Suppose that this is a time duration of the signal and this is a time duration of the channel, and hence the bandwidth of the channel is more than the bandwidth of the signal. Then how RT will behave? The bandwidth of the RT will behave. If we see that if the bandwidth of the signal is less than the bandwidth of the channel, then over the whole bandwidth of the interest of the signal, the channel will remain constant. So, you are expected to get the same amount of the amplitude change and the linear phase change over the whole bandwidth of the transmitted signal. Hence, we call it a flat fading. You won't see any kind of the dispersion happening in the frequency spectrum of the received signal while passing through such channel. So, it is a relative relation of the bandwidth of the signal and the channel. Based on that, the flat fading phenomena happens. Opposite to this is a frequency selective fading, when actually we see that the bandwidth of the signal is more than the bandwidth of the channel considered. In such a situation, channel can never give you the uniform amount of the amplitude change and the phase change over the all frequency band involved in the signal spectrum. Hence, you are going to get a different amount of the different shape. The shape itself or the frequency components itself will be partially present and partially not, and different kind of the amplitude reduction and the phase changes are happening over the incoming signal. we call it frequency selective fading. See, the portion of the incoming signal, transmitted signal here in this zone, I have got the completely different amplitude changes compared to that where channel is really present. We call it frequency selective fading. Fading can be also very fast and or very slow based on that. If we are having a very high speed for the movement, then actually channel is expected to change very fast over the time axis. So, coherent time of the channel will be very, very small, as your Doppler spread bandwidth will be very high. So, you are expected to get very fast changes, and accordingly you have to design the signal processing in the receiver. Opposite to that is the slow fading. If you are moving at a moderate speed or a very slow speed or in a pedestrian speed, here you are going to see actually the large coherence time over which the channel is showing the constant effect, and you are not going to see a large amount of the changes in the received signals profile. And hence actually the processing and the corrections of the due to the fading is less, that it is less loaded. I mean, the receiver processing will be less loaded in such situation. This is a picture which talks about the combined effect when the transmitted symbol period versus your RMS delay spread value of the channel. Actually, if you are and you are having a coherence time involved in it, if you are having a low coherence time, you will get a frequency selective slow fading if your transmitted symbol is comparative to the RMS delay spread. And based on this combination of the TC, TS and sigma tau, you will get the whole portion can be divided into 4 parts about the flat slow fading, flat fast fading, frequency selective slow or frequency selective fast, based on whether you are crossing the TC, how high TC is or how big the TS values are, and where is actually the location of this RMS delay spread. Similarly, in the bandwidth based in the frequency domain, based on the transmitted baseband signal bandwidth, Doppler spread as well as the coherence bandwidth, your signal bandwidth, the same division is possible. So, this is a time domain division and this is the equivalent frequency domain description, but fundamentally you can have any 4 of this combination when you are transmitting over a frequency over a wireless channel. So, we have to actually be very, very careful when we are designing a transceiver, and we need to know the channel, kind of the channel we are dealing with, whether it is a flat fast or the flat slow, or it is a frequency selective fast or it is a frequency selective slow channel.